All right, thank you, Victor. So before we get started, I would like to thank Victor Magri, who's our volunteer helping out, and he is our host of the meeting. So any problems you have, you can contact any of us co-hosts, but also Victor as well. So this is a tutorial meant to cover overview and use of some of the newest features in Sundials, which is a suite of time integrators and nonlinear solvers that's being developed through the ECP. My co-authors who basically are handling the majority of the tutorial are Cody Bayless, David Gardner, and Daniel Reynolds. You'll hear from each of them in turn. So today we're going to cover a little introduction, and then we're going to go into a little more depth on multi-rate time integrators, enhanced GPU support, new performance profiling, analysis, and logging tools that have been developed. And then Dan's going to cover a demonstration code that's been developed to show some of the flexibility of some of these new features of Sundials and use on some of the hybrid GPU systems that we're targeting. If you want to get a copy of this tutorial in PDF form and follow along, you are welcome to do so at this page. This is the Confluence page for our Sundials project under ECP. In particular, we are work package 2.3.3.12, which in ECP parlance makes it much easier to find on the Confluence page. You're welcome to do that. If you're not part of the ECP and you would like a copy, I'll have some links at the end that I'll show where we will upload a copy of this tutorial after the fact. Okay. So this is not animated. Interesting. Okay. All right. So Sundials is a suite of nonlinear and differential algebraic equation solvers. This is a library of ODE and DAE integrators and nonlinear solvers. It has 6 packages: CVODE, CVODES, IDA-S, ARKODE, and KINSOL. And I'll say a little bit more about each of those in a moment. It is written predominantly in C with interfaces to Fortran. And Python will be coming soon. It's designed to be incorporated into existing codes, meaning that we don't provide a full framework to build an application on. We try to be a pretty specialized set of tools that can be brought in to handle the time integration in nonlinear solvers. Through the ECP, we've been developing a rich infrastructure of support on exascale systems and applications. We're freely available, released under the BSD 3 clause, and had over 100,000 downloads in 2021. We have a very active user community that's been supported by our Sundials users email list. So if you have, you're starting to use Sundials and you have questions, that's a great place to post some questions to. We as developers, we do monitor this, but also we have a very active community of very helpful and constructive users who help each other out as well. We have detailed user manuals included with each of our packages, and also new this year, we are on Read the Docs and have full online documentation there as well. So the 6 packages, as I mentioned, are listed here. And the thing to note is that we've abstracted out of the integrators an interface to nonlinear solvers, to linear solvers, and all operations on data. So the integrators don't really know exactly what kind of nonlinear, the specific nonlinear solver or linear solvers that are being used under the implicit integrators, nor does it know, do they know anything about the layout of the data underneath them. So that's all been extracted out, and those can be all user supplied, or you can use some of the native structures that we provide. All parallelism is also encapsulated in the vector and solver modules and user supplied functions. And so the integrators know that they run on CPU, and that's pretty much it. You can find much more information about Sundials on our website at LLNL, given here. So we've been used worldwide in applications from research and industry. Significant use in the ECP. There's the cosmology, the NIX cosmology code, the Pele suite of codes for combustion. The E3SM code has used Sundials in development of the non-hydrostatic dynamical core. The NEC 5000 code has used Sundials, and then a host of other applications as well worldwide. Also, we've been released in several third-party packages. You can find us in the Red Hat Enterprise Linux distribution, SciPy, and the Cray TPL, or TPSL, sorry. So Sundials offers packages with linear, multi-step, and multi-stage methods for time integration. So CVODE and IDA were the first time integrators in Sundials, and they're based on linear multi-step methods. They also have forward and adjoint sensitivity analysis variants. So CVODE is the ODE integrator, IDA is the DAE integrator. They're both adaptive in order and step size. And both packages include stiff integrators, and CVODE includes non-stiff integrators as well. ARKODE was developed to handle one-step multi-stage time integration methods. So it was originally designed to solve systems that look like this, where now M of T may be the identity or any non-singular and optionally time-dependent mass matrix. So similar to, or often use cases that come from finite element methods give rise to need for that. Multi-stage embedded methods give rise to adaptive time steps within ARKODE. And then ARKODE is built around three stepper modules that provide the actual evolution from one step to the next. And the first was ARKStep, which has explicit, implicit, and additive IMEX Runge-Kutta methods. ARKStep, which has streamlined explicit Runge-Kutta methods. And the newest is MRI-Step, which has multi-rate infinitesimal step methods. And Dan will talk much more about that in just a moment. And lastly, we have some parallel and time support through use of XBraid. So we have now wrappers for Sundials, vectors, and explicit, implicit, and IMEX methods to be used in the XBraid multi-grid reduction in time, parallel and time package. And then KINSOL solves nonlinear algebraic systems with Newton or accelerated fixed point methods. We won't say a whole lot about KINSOL in this talk today. Time steps in general for Sundials are chosen to minimize local truncation error and maximize efficiency. A lot of folks use Sundials because we are adaptive and we can be very efficient because of that. I won't go a whole lot into that here today. I just want to point out that our error norms and things that we work with in Sundials are actually a weighted norm, where the weight includes information about a relative tolerance and absolute tolerance that's supplied by the user. And the absolute tolerance can be a vector, so it can be component specific. And this careful choice of these tolerances is what can give us a lot of efficiency and choice of in choosing time steps. So again, I don't want to go into a lot of depth here on that. I just want to mention this. And then Sundials uses what's called modular design and control inversion to interface with application codes, external solvers, and encapsulate parallelism. It's a lot of nice words that basically means that control passes between Sundials, the solvers that it calls, and the application code that calls it back and forth as the integration progresses. And this is done through callbacks. In general, you might have an application code that handles your discretization and your relevant information. It will provide a right-hand side function, F. It may provide Jacobian information if implicit integrators are used and a Jacobian is supplied. It may provide a preconditioner. Usually these are application-specific things. And then that information goes to the time integrator, and it can go into the nonlinear solver and linear solver as needed and appropriate through the callbacks that are done. And again, nonlinear and linear solver modules are designed for generic systems. So the integrator calls these generic interfaces, and then those can interface to specific solvers underneath. Okay, I don't want to say much about this slide except to note that we've done a lot of work for pre-exascale environments and exascale environments. That's kind of outlined here on this slide. This is included in the slide deck, but David will go much more into depth on all of the different supports that we have for GPUs in just a moment. So what's new in Sundials? High order multi-rate methods that can integrate different portions of the problem with different time step sizes, including implicit and IMEX methods at the slow scale, custom integrators for the fast scale to allow much more tailoring to specific applications. And then new vector and solver support for sickle-based applications is something that's come in the last year. That's done through direct sickle vector as well as Raja with sickle backend and 1MKL dense solver support. We also have support for logging, much more run diagnostics than we've ever had before, full time step histories and things like that. Cody will talk a lot more about that in his talk. We also have performance profiling, and then we added a feature a couple years ago to CVODE to project the solution onto an invariant manifold. That's been carried over to CVODES. And then, as I mentioned, we have new online documentation at Read the Docs, and then we've also now moved our development repo fully to GitHub. And that's something that actually happened a couple weeks ago. So what are we working on now? Greater support on AMD and Intel GPUs, including optimizations for our vectors and interfaces to more batch solvers. Python interfaces, as I mentioned, for our integrators and KINSOL, more multi-rate methods and options, and then greater interoperability to discretization packages. So I want to mention our team here. Folks that you may know through the Xscale computing project, Cody Balos, David Gardner, and Dan Reynolds, and myself are all part of the ECP, and we're present today and at the meeting all week. We have a new postdoc, Stephen Roberts, who's joined the team as well. And that's all I had for an overview. Are there any quick questions before we moved into multi-rate time integrators? All right, so Dan, you want to take over?
Sure. Can everybody see that okay?
Yes.
All right. Okay, so so as Carol mentioned, I'm going to talk about our multi-rate time integration stuff, what we've been adding in the last couple of years. So maybe before I talk about what we've added, let me just kind of define what multi-rate time integration really is for those of you who are a little less familiar with the nomenclature. So multi-rate methods will consider a general initial value problem that'll have an additive form typically, where we think of splitting the right-hand side into two components, a slow component and a fast component. And that slow component will be all of the operators inside of the physics that we would want to evolve with a slow time step size, capital H. And then the rest of it we think of as happening at a faster time scale. And so those we might want to evolve with smaller steps that are little h that are much smaller than big H. And so people often think about these as subcycling methods, where you want to subcycle the fast dynamics underneath the slow dynamics and that sort of thing. So multi-rate methods have been around for decades. They typically take the form of operator splitting approaches with subcycling. And so the standard approach that most folks are used to is called Lee-Trotter, if you even know the name for it, but you might just call it operator splitting, where to go from a time step yn to yn plus 1, you would first evolve one operator, be it the fast or the slow, either whichever you'd like, over the full time step with the correct initial condition. And once you're done evolving that up to the time tn plus 1, you take the result of the first integration, and that becomes your initial condition for evolving the second operator. And so one of these might be one backward Euler step, and the other one might be 1,000, Runge-Kutta sub-steps or something like that. When you're done with the second operator, you call the result of that your updated time step solution. And so, one obvious thing here is that you're saying the initial condition for this second operator, which you're essentially supposed to define at the time tn, is somebody else's answer at a completely different time. And so this offset in time can give rise to some lower accuracy. And typically, Lee-Trotter is only going to be first order accurate at best. People will try to improve that slightly, and you can do what's called straying splitting or Straying-Marchuk splitting, and that will symmetrize this kind of loose initial condition coupling to achieve second order by, say, taking a half of operator F1 over the full step for F2, and then a half of the F1 again, and playing similar kinds of tricks. And so in recent years, people have worked to build higher order versions of these multi-rate types of approaches. And so I'm going to focus on the infinitesimal family of multi-rate approaches here, and some references are kind of up at the top. Multi-rate infinitesimal step methods, which have multiple acronyms, but most people are calling it MRI now. They arose in numerical weather prediction, but they've really taken off in the last couple of years. The idea behind them is you want to evolve the fast time scale using whatever algorithm you'd really like. So like a subcycling approach, as long as that subcycling approach is sufficiently accurate, you'll be fine. And at the slow time scale, that's going to be advanced through essentially defining and then solving a sequence of modified fast initial value problems. And so we'll look at a skeleton of the algorithm on the next slide to kind of nail this down a little bit. But the way these achieve higher order, they can be third or even fourth order, is they use that kind of initial condition coupling at by defining the initial condition for each of these fast initial value problems. But then they also help propagate information from the slow time scale, FS, onto the fast time scale through essentially doing a temporal interpolation of that information. And again, we'll see how that looks on the next slide. These kinds of methods can be quite efficient. You can get high order, third or fourth order, by only traversing the time step once, which will be unlike some extrapolation or deferred correction techniques that might still achieve high order, but they need to do that time step over and over again, which can be significantly more costly. And so kind of the way this looks, if you are familiar with Runge-Kutta methods, think Runge-Kutta, you're going to have stages Z1 through ZS. The first stage is your old time step solution, Yn. For all the remaining stages, the first thing you do is you define a forcing function, R of tau. And this really is just a linear combination of slow function values. And in general, these are previously computed stages, Z1 through Zi minus 1. And so you're going to kind of glue together old values of f slow using coefficients that are time-dependent functions that we'll talk about in a second. After you define this function, it's really only a function of time. You then solve these fast initial value problems. And so the way this differs from the Lee-Trotter approach is it's not just solving an ODE for f fast, but you also include this forcing function that brings slow information onto the fast time scale. You solve these over subsets of the overall time step. And so these C's are typically sorted from lowest to highest, with the initial condition being your whatever previous stage solution you had before. After you've solved that fast initial value problem over that subset of the time interval, the result of that is your new stage solution, Zi. And so when you're done with all the stages, your updated time step is your final stage solution. And so it feels a little like the Lee-Trotter approach, but it has this forcing term that really helps propagate information between timescales. These coefficients, gamma ij of their argument, are polynomials in that argument. And those polynomials are defined by coefficients that need to satisfy various order conditions to get third or fourth order accuracy. When two successive C's are the same, notice this time interval shrinks to 0. This fast time step evolution problem becomes just a standard explicit Runge-Kutta or diagonally implicit Runge-Kutta kind of update that you'd normally do with implicit or explicit Runge-Kutta methods. And so when you have implicitness, that's defined by having one of these guys, the gamma ii. So notice we're going to define ri using zi, and that becomes zi down here. So there's a coupling there. When that happens, you typically only do that when the two neighboring C's are equal. And so you have either a Dirk solve or a fast evolution, but there don't really exist methods where you both have to guess the fast stage solution, zi, then solve an ODE and hope that you end up at the right answer. So that would be a solve coupled approach, and those aren't really present. But this solve decoupled approach, where you alternate between implicit solves that are Dirk-like and fast evolves that are kind of subcycling-like, are pretty standard. So in Sundials, we have these inside of ARKODE, inside the MRI step module. And so that supports explicit treatment of the slow time scale, implicit treatment of the slow time scale, or even IMEX treatment of the slow time scale. And so here the idea is you have your fast dynamics, whatever that is, but the slow you can decompose into implicit and explicit components. And as we'll see in the demonstration code a little later, this could be diffusion, that it's stiff, so you want to solve it implicitly, but it doesn't really propagate super rapidly. And FE might be advection, that isn't stiff, but you need to make sure that you resolve those kinds of operators, but you don't want to do that implicitly. And so we would evolve both FI and FE using these big step sizes H, and then F fast is subcycled. That slow time scale can be handled using explicit, implicit, or IMEX MRI GARC methods, as I mentioned a moment ago, and they can have orders of accuracy 2 through 4. Additionally, if you know what kinds of MRI GARC method you want to try out and we don't have it yet, or you want to invent some new tables that satisfy order conditions and plug them in, we'll just take the coefficients from you and run with them. It's better kind of maybe for people who invent them and they can try them out easily as opposed to end users, but you're welcome to try that out as well. At the moment, the slow time scale needs to be user defined, this slow step size, and you can change it between time steps. The fast time scale is solved using ARKStep, this IMEX additive Runge-Kutta approach, or explicit or implicit that Carol mentioned earlier, or you can plug in your own, and I'll have a slide on that in a moment. Robust multi-rate additivity, so where we adapt both the slow and fast time step sizes to meet accuracy tolerances, is under development. Alex Fish and I submitted a paper on this earlier this year, and we hope to have this in MRI step within the next year. So how does it look when you run these things? I'm assuming there's a baseline knowledge of how kind of Sundials integrators look, and if you need a little background knowledge, we have another tutorial we can point you at from a couple of years ago. But the basic premise is we're going to first create the fast integrator. And here I'm using an implicit integrator at the fast time scale. So there's no explicit component, but there is an implicit component. And you give the initial conditions for that fast integrator. We'll see this CTX concept a little later. Cody's going to talk about the new Sun context object that we have inside Sundials. After you create the fast integrator, which knows about the fast timescale of the problem, you set whatever options. So here would be the linear solver, nonlinear solver, however you'd like to solve the implicit problems that come at this fast timescale. After you configured that fast integrator, now we wrap it up as what's called an MRI step interstepper. And we have a utility routine that will do that if the integrator is an arc step integration. So you pass by the memory structure for the arc step integrator, and it gets wrapped up as an interstepper structure. Alternatively, if you want to make your own and have a custom interstepper, then you wouldn't create arc step here, but you would create your own MRI step interstepper object. And we'll talk about that in the next slide. After you have this interstepper constructed, now you create the MRI step overall multi-rate module. You tell it how to do the slow time scale. Here's the explicit and implicit components at the slow time scale, the initial condition for the slow time scale. And you hand it the integrator you want to use for fast time scale subproblems. Then, of course, you set that up appropriately. Here would be the nonlinear solver stuff you'd like to use for FSI, that sort of thing. And after everything's all configured, you evolve like normal. And so we evolve up to some time T out. And we're going to do normal mode, so we take internal steps until we pass T out, and then we're going to interpolate that sort of thing, like all the other Sundials time integration. So this is kind of how the code looks. We can ask questions about it, certainly, and we have example problems. The one up at the top is where I kind of extracted these from. A few more comments about MRI. So we have some custom intersteppers. You can supply a custom interstepper, and they have a pretty simple API. We have to solve these modified initial value problems. So your custom interstepper has to be able to evolve to solve over some time interval with some initial condition. We also want to be able to evaluate the fast right-hand side function. Notice that wasn't supplied to MRI step here. We don't see FF anywhere. And so we need to be able to call the FF at the MRI step level. And that's really just to do dense output for certain ways of doing that's output in MRI step. And then optionally, you can have a reset function that will reset the initial condition for a fast integration. And so we can talk more about that if you'd like in a little bit. We have an example program inside of the Sundials repository that actually packages CVODE as a custom interstepper for MRI step, in which case, and David put this together, it does all these parts, and you can kind of see exactly what's required to build your own custom interstepper. And it kind of shows you step by step how to make that happen. And then, of course, as we mentioned already, I'm going to discuss another multi-rate example at the end of this tutorial when I talk about our scalable demonstration code. And there again, we have a custom integrator that I'll talk about at that time. So I'm going to hand off to David now. I think I went about 30 seconds over time, so I'll be quiet and we can ask some questions a little bit later. Thanks.
Okay, thank you, Dan. Yeah, so we're going to talk about Sundials GPU capabilities now. My slides will progress. There they go. Okay, yeah, so as Carol mentioned in the introduction, Sundials is built on an object-oriented design. And so what this means is that we can support various different types of GPU hardware and GPU programming models by having different class implementations used underneath Sundials. And so we currently have classes that support all three of the vendor's hardware. And so what that really means is that to use Sundials on GPUs, you really need to do sort of three things. One, you need to build Sundials with GPU capability turned on. And so for example, turning on HIP. Then when you write your program that uses Sundials, you need to use the classes that are GPU enabled. So for example, like the HIP vector or HIP compatible solvers. And then finally, the callback functions for doing things like computing the right-hand side or filling Jacobians, those sorts of things. Those callback functions need to launch kernels and do the computations on the device. And so we can kind of break down Sundials use cases into two sort of primary groups. You've got where Sundials is driving the main time integration loop. And so this is like large ODEs that are finite difference, finite volumes, finite element sort of computations. And then the other use case is where Sundials is used to evolve sort of local reaction systems within a larger problem. So think of like a combustion problem with AMR and doing those local reactions with Sundials. And sort of the key considerations to think about when using Sundials on GPUs is that Sundials doesn't migrate data between the host and the device for you. And so it's up to the user and the callback functions and the classes that are used to ensure data coherency between the host and the device. And for performance considerations, you want to minimize any movement between memory spaces, ideally keeping the data resident on the device throughout the stimulation. The Sundials provided GPU-capable classes, so the vectors, the matrices, and the solver classes, they all keep data resident on the GPU device. So what this means is that when control passes from the user to Sundials, Sundials expects the data to be up to date in the device memory. And then going the other way around, when going from Sundials back to the users should expect the data to be updated only in the device memory. And so moving into these Sundials classes that support GPUs, first we'll talk about the vector class. So Sundials has a variety of vector implementations that support GPUs. We have a HIP vector, a sickle vector, a CUDA vector for the native programming models, as well as a interface, or as well as a vector that uses Runge and supports the CUDA, HIP, and sickle backends, as well as a vector that supports OpenMP device offloading. There are a couple other vectors that are actually sort of wrappers of subvectors. So there's the many vector, which Dan will talk about more later on in the tutorial, which operates on a collection of vectors, and so it can operate on subvectors that are in different memory spaces. And then there's the MPI plus X vector, which can wrap a local vector to provide working in the sort of the MPI plus X paradigm. So the native Sundials vectors have various sort of special features that can support either separate host and device memory spaces or unified virtual memory. There's also the option to supply memory allocators from the user side of things, as well as to supply user-defined execution policies. And I'll talk about these three things more in a couple of slides. Also, if you want to provide your own n-vector implementation, that's straightforward as well. And that's something that other libraries do. For example, AMRX and Samurai both have their own n-vector implementations that they provide for users to leverage. So how do you create a Sundials GPU-enabled vector? Well, there's two common constructors. There's these new and make constructors, and so these create vectors of some given length, either by allocating their own memory in the new case or taking user supplied pointers in the make case. And both of these are for separate host and device memory. If you'd like to use unified virtual memory, then you would use one of these constructors, which generally take a length, a context, and possibly either allocate the data themselves or take a user supplied pointer. I'll note that in these names here, star can be any of the HIP vector, the sickle vector, the CUDA vector, the Runge vector, or the OpenMP dev vector. Slight note on the sickle case, all of these functions also take a sickle queue. And then currently the OpenMP offloading vector only supports separate host and device memory spaces right now. And so I'd mentioned previously that there's also the option to supply your own allocator. And so there's a separate constructor for that, which uses this Sun Memory API. So in this case, you create a new vector with a memory helper. Again, it takes a length. It takes whether you want it to be managed memory or separate host and device memory. And then a helper, which takes care of sort of memory operations and then a Sundials context, which Cody will talk about a bit more later. So what is a Sun memory? Well, a Sun memory is just a structure that holds a void star data pointer, the type of the memory that it's in, and then an ownership flag for that pointer. And then the Sun memory helper class provides the sort of operations that we typically need for acting on a Sun memory type. So for example, there's functions that it provides to either allocate or deallocate memory of a given type and size. There are copy functions, either synchronous or asynchronous, to move data between different memory spaces. And then there's clone and destroy operations to either create duplicates of the helper or to free them when we're done with them. And so we package up native implementations using HIP, sickle, and CUDA, and these can be used with the HIP, sickle, CUDA, as well as the Runge n vectors. And then this is a nice interface that a couple of libraries like AMRX and MFEM have leveraged to be able to use their own memory tools underneath Sundials objects. So all of this sort of memory pooling capabilities they have can be leveraged by the native Sundials vector objects. So sort of the last special feature that I'll talk about is the option to supply user-defined execution policies. And so these enable supplying an object that tells the vector what the kernel launch parameters should be, the grid size, the block size, those sorts of things, as well as the stream, and then switching between different implementations of reduction operations, which can be very critical depending on the hardware that you're acting on, or the hardware that you're using, which sort of implementation of the reduction operations that you want. Similarly, setting the stream can be very helpful when you're running multiple instances of the integrator in parallel, and then you want them to do operations in different streams so that you can gain some additional currency between the different instances of the integrator. And I'll have some examples here at the end, sort of highlighting this use case. And so we have native execution policies provided for HIP, SYCL, and CUDA. So there's two sort of streaming operation policies. These are thread direct and grid stride policies. So whether you divide up the work with sort of one unit of work per thread, or whether the thread has multiple units of work that it needs to handle. And then similarly, there's a block there are two reduction policies. These are either a block reduce that uses atomic operations, or a block reduce that relies on shared memory. And so choosing between these can be very important depending on what the hardware has support for. For example, if it has support for hardware atomics on doubles. And so once you create a vector, you can create an execution policy using one of these constructors, and then there's a kernel and there's a set function for each of the HIP, CUDA, and HIP, CUDA, and SYCL vectors to attach those policies. Right. So here you swap out ** for CUDA, HIP, SYCL, whichever one you're using. So that covers the vectors. As was mentioned earlier, Sundials has several implicit time integration methods. And so in these cases, the integrators need to solve either one or more nonlinear systems per time step. And so for this, Sundials provides implementations of Newton's method, as well as an Anderson accelerated fixed point solver. And these all follow the Sun nonlinear solver interface API. And in both of these cases, the native Sundials nonlinear solvers both leverage the underlying vector and user callback functions for the GPU capability. So if you use a CUDA vector and you launch CUDA kernels, then the nonlinear solver is CUDA capable. Similarly for HIP or SYCL. If you want to supply a specialized solver for your application, that's also possible. You can wrap up any user supplied or external solver as a Sun nonlinear solver implementation, and I've got a pointer here to a example problem that does a advection reaction problem with a task global nonlinear solver for the reactions. And so by default, the integrators use Newton's method as the nonlinear solver, and so this requires selecting a linear solver to use beneath the Newton's method, and possibly a matrix object to go with that solver. So Sundials provides two classes of linear solver implementations. There are matrix-free Krylov solvers, so GMRes, FGMRes, precondition conjugate gradient, those sorts of things. And like the nonlinear solvers, these classes inherit their GPU capability from the underlying vector object, as well as from the user supplied functions like the ODE right-hand side or the preconditioner. And then the other class are direct solvers. And in this case, we provide linear solver objects that wrap GPU capable linear solvers from either from the vendors or from external libraries, and I'll talk about those in a second. Like with the nonlinear solver, if you have a specialized linear solver that you'd like to use with your application, it can be wrapped up as a linear solver object and provided to the time integrator. And I got a pointer to an example here that shows a problem wrapping a iterative solver from Hyper and using it with CVODE. So if you'd like to see how that works. So talking a little bit more about the direct solvers that we supply batched solvers from a variety of either the vendors or third-party packages. And so these are targeting block diagonal systems specifically. So when we have the case where we group up several independent problems into one larger problem and evolve them together, so I think that's sort of use case 2 that I mentioned earlier, you end up with a block diagonal system. And so that's well suited to these batch solvers. In the case where the blocks are dense, we have options of Magma, which supports either HIP or CUDA. And I'm sure in the future we'll support SYCL as well. And currently for SYCL, we have the one and interface to the one MKL batch solvers for DP C++ problems. In the case where it's sparse blocks, there's an interface to the Q sparse batch QR solver that's also available. And something that's in the works right now is an interface to Ginkgo, which will supply both sparse and dense batch iterative solvers rather than direct solvers. And then that'll support HIP, SYCL, and CUDA as the backends. All right. So what does it look like to use one of these solvers? Well, we'll look at Magma specifically, but it's very similar for the others. Well, first, we need to create that block diagonal matrix. So we need to tell it how many blocks we have, the size of those blocks, N&M, the memory type, whether it's device or shared memory, or sorry, UVM, the helper, the memory helper object that's going to go with it. This void Q, this would be your HIP stream or your CUDA stream, depending on which backend you're using with Magma, and then the Sundials context. And so once you've got this matrix set up, then you can set up the linear solver using the vector and using a template vector and matrix in the Sundials context. In the case where in this block diagonal case, all of the blocks need to be the same size. We don't support separate block sizes right now. In the sparse case, all of those blocks need to have the same sparsity pattern. And also when you're using one of these batch dense solvers, you'll need to supply from the user side of things a Jacobian function to be able to fill in the Jacobian matrix. Ideally, this should launch a kernel to do it, but you could similarly, fill it on the host and copy it over, but that would not be as performant because you want to leave memory on the device as much as possible. And so the setup for the SYCL case is almost the same. Swap out Magma for one MKL, swap out void Q for SYCL Q, and you've got the same sort of setup. All right, so I'm going to take a quick sort of trip through a high-level look over a example that uses sort of these solvers to do this sort of grouping strategy, where you're doing several independent local solves or local evolutions of a system, but they're small, so you're going to group them together into a larger system to be able to leverage the device better. And so we're going to look at this sort of 3 species Robertson's kinetics problem, where we've got sort of three independent, we've got a system of 3 ODEs, and then we're going to do several of those systems together. So we're going to have n groups of those. When we group them together, we'll have a total of 3 times however many groups system size that we're going to evolve forward in time. So we're going to look at solving this with CVODE using a BDF method with the modified Newton iteration and then the Magma dense solver. So I'll be focusing on Magma using HIP, but there's also a CUDA version of this as well as a DP C++ version and then a CUDA with Q sparse version. If you want to see those, they're all very similar, mostly just changes in the names that you call on how to use them. Right. So let's first start out with the user supplied functions. The user needs to supply a right-hand side function for computing y prime equals f of ty. And so this computes that f of ty. So also what this user supply callback really does is unpacks a user data pointer, which is whatever user data they need to do the operation, grabs the data pointers out of the input and output vectors, determines what the kernel launch parameters will be, and then calls some kernel to do the work. And so that's that. And so that's this F kernel, which just loops over each of the groups, or which just where each thread and where each GPU thread is evaluating one of the group's right-hand sides. Similarly, we're going to have to supply a callback function for computing the Jacobian. So like the right-hand side function, The callback function that's handed to Sundials sort of unpacks the user data, unpacks the vector and matrix data, determines the kernel launch parameters, and then calls some kernel to do the actual filling of the Jacobian matrix. And so that's what this J kernel does. It goes through and each thread fills in one block of the Jacobian. And so now we've got our user supplied functions. Now we need to set up our GPU enabled objects. So first thing we're doing is going to create a Sun context. Cody will talk a little bit more about this later on. I'm going to set what our problem size is. So our group size is 3 times however many groups we have. And so that's the problem size we're actually solving. We're going to create a HIP memory helper. We're going to create a HIP end vector of the size of the total problem. Then we're going to fill that. We're going to fill that HIP vector with the E. We're going to fill that HIP vector with the E initial kin addition. In this case, we're doing it on the host and then copying it over to the device. But you could just as equally launch a kernel to fill this in directly in the device memory. So we've got our vector. We've got our vector filled in with starting values, and now we're going to make our matrix. We've got n groups that we're going to solve. The groups are each 3 by 3. In this case, we're going to use device memory. We're going to hand it the helper that we created earlier. We're going to use the default stream here. So we're going to pass null, and then we're going to set the Sun context. Now we've got our vector and matrix object set up. So we're going to create the Sun linear solver to go with it. So now we've got all of our GPU objects made. So we're going to set up CVODE. We're going to do BDF method. We're going to hand it the callback for the right-hand side. We're going to hand it the initial time, the initial vector. We set up our user data, attach it to CVODE. We're going to set up our tolerances with CVODE. We're going to attach our linear solver and matrix that we created earlier. We're going to attach our Jacobian function for filling in the Jacobian. And then we're going to loop over some output times, calling CVODE to evolve forward to T out. It'll fill in the output vector Y and the return value and then the return time. And it'll do this in normal mode, taking several time steps or however many time steps it needs to reach the output time. If we want to output the solution, we'll copy the data back from the device to the host, do whatever output we want to do. And we'll do this until we reach whatever our final time is. And then we'll do a print of the CVODE stats from the end. And then once we're done, we'll destroy whatever objects we've created. So really quickly, you can also do, so that was just using one GPU stream, just the default stream. You can similarly set this up with multiple streams to do multiple instances of CVODE operating concurrently to each other. In that case, we just need to create arrays of objects rather than just one object. So for example, I create an array of Sun contexts, create an array of memory helpers, an array of vectors, right? And each of those is paired with some particular HIP stream. I set up execution policies that use those streams. I attach those execution policies to the vector, attach that stream also when I create the matrix, and then I set up the linear solver. So the same as before, but I've just got arrays of things for each stream that's going for each OpenMP thread that's going to be tied to a GPU stream. And so here we get to the parallel for where we're going to loop over our groups and have these CVODE instances running in parallel. Going to fill our initial conditions. If we haven't set up CVODE before, we're going to set up the CVODE for this thread and stream, and then set up CVODE like we would in the prior version of the problem. If we've already done it, then we just need to reinitialize CVODE for this new group. And like before, we'll loop over the output times just using the right CVODE memory and vector that go with this stream and thread. Output solutions, print integrator statistics, just like before. Right. And that's a quick sort of overview of the Sundials GPU capabilities. I'll turn it over to Cody to talk about some of the performance analysis and logging features.
Yep, thanks, David. Share here.
I'll take this moment to remind folks, if you haven't signed in, to sign the Google Doc sign-in sheet. The link is in the chat. I'll go ahead and paste it in there again in case anybody missed it.
Thanks, Carol. Okay, so I'm gonna first, I'm gonna talk about some of the performance profiling, analysis, and logging capabilities that we've added to Sundials in the last year or so. And so specifically in Sundials version 6, we included a MPI-aware performance profiler, the Sun Profiler class. It has low overhead and when enabled, and no overhead when disabled. You can choose this at build time if you want to enable it or not. Key regions within the time integration loop are profiled out of the box if you enable this. And there's an environment variable and runtime API that you can use to control output. Optionally, for more advanced profiling, you can substitute caliper underneath this. I'll show in a minute. It's just as simple as a couple, again, build time options that you have to set, and then you can use caliper. In Sundials 6.2.0, which we released just a couple of weeks ago, we've also added some new functions for printing statistics out from the integrators, and also a logging capability under the SunLogger API. The print all stats functions allow you to choose between human and machine readable formats. So you can print out to machine readable and then use scripts to parse these statistics. The logger, you choose the max logging level that you want to enable at build, that you want at build time, and this minimizes overhead during runtime. And you can actually completely disable it currently. There's separate channels for error information, warnings, informational output, as well as debugging output. And for informational output, we've added a lot of statements within Sundials that log internal decisions by the integrators and state to help with debugging methods or seeing how they're performing in your application. Again, like the profiler for the logger, there's an environment variable runtime API that you can use. And so together, these features all really make analyzing and measuring Sundials performance easier than ever. And now, before I go further into those, I will unwrap the mystery of this Sun context that we've seen earlier in the tutorial. And so in Sundials 6, we added this Sun context object that all of the Sundials objects, such as the vectors, linear, nonlinear solvers, the integrators, matrices, they all hold a reference to this context. And this facilitates the profiling, logging, some error handling features that we're going to be introducing soon. And it really ties together the objects of the Sundial simulation. And so this Sun context represents a Sundial simulation execution context. So if you, for example, maybe had the multiple thread situation that David showed, you would want to have a Sun context for each thread. And creating one is simple. So it's the first thing you should do when you're using Sundials. The first call you should make is to create this Sun context. And you create it, and then you'll pass that to your other objects. In this example, I'm showing the C API, the Sun context create function. Maybe in a couple of examples that David showed, you notice there is a Sundials : context, which is the C++ interface to this Sun context, which it is RAII compatible. And so if you have a pure C++ code, you might like to use that Sundials context wrapping. Now back to the other features for profiling and logging. So in this demo, just show how easy it is to enable profiling with Sundials now. So simply clone Sundials, a CD into the Sundials repo, make a build directory, and then I just run cmake, and with the critical part, this -d Sundials build with profiling on. And so that enables profiling. You notice there's a little warning down here that building with profiling, performance may be affected. Really, usually with profiling, it's pretty small overheads, but it should be, looked at in your application. If you're trying to have the most high performance run, you probably should turn profiling. After this, you're going to set an environment variable. If you're using the environment variable API to turn on the output or direct it to a file, and then you just run your code that uses Sundials. And for example, with a Sundials example, this is in the ARKODE C serial directory in the repo. There's a link down here. So you just set some profiler print equals to 1. This will give us output to the standard out, and then ARKanalytic example. And then at the end of the run, you'll get this table here, and it shows inclusive timings using the built-in Sundials profiler for all these different regions that we've marked up within Sundials. So you can see the arc step evolve took 97% of the time. Of course, that's inclusive, so everything like the Sun nonlinear solve is included in that time as well. You have a maximum time for MPI rank and an average time for MPI rank. course, this example is just one rank, so these are the same. And then there's a column with the count of calls to that function or region. And with the sunfiler print variable, settings to 0 disables output, but note it doesn't disable the profiling itself. So whatever overhead from the profiler there is will still be there even if you disable the output. As I mentioned, you can also set this variable to be a file name, and then the output will go to that file instead. So the Runtime API for the profiler allows you to configure profiling or also add profiling regions to your application code. And so, for example, in this code, the first thing you do is either create a Sun profiler object, or in this, we're getting the default profiler that's created as part of the Sun context. You can store it in the user data for the application then. And then in this right-hand side function, this diffusion function, which is the right-hand side for this example, you could then get the profiler out, and then you can mark up this right-hand side using this macro Sundials CXX mark function. There's various other macros that you can use too that are documented in the Sundials documentation. And now I'll show what the output looks like that in a second, but to show how we can use Caliper as well, I'll show that on this slide, and then we'll look at the output. So Caliper is a program for instrumentation and performance measurement, it is a program instrumentation and performance measurement framework. To use Caliper with Sundials instead of the native profiler, you just need to install Caliper and then build Sundials with enable Caliper on, tell it where Caliper is, and then you still need the Sundials build profiling node. After that, you can use the Caliper environment variables to configure how it runs. And so here, running this ARKODE diffusion to the MPI example, we're telling Caliper with this Cali config environment variable that we want to runtime report. And what does that look like? Well, it gives you a much more detailed tree with exclusive timings. And there's actually many, many different things you can do with Caliper, but this is just one of the simplest ways you can use it. But you can see now the diffusion function that we marked up is showing up in the timings along with all of the other parts of Sundials. Again, there's a link to this example down here, and a link to the documentation will be provided in a little bit. So moving on to the logger for Sundials. So similarly to the profiler, you can disable logging at build time or enable it at build time. And so what you want to do is configure CMake when you build Sundials with this Sundials logging level option. And a value of 0 will give you no logging. 1 will give you errors, 2 errors and warnings, 3 errors, warnings, and informational output. And then 4 will give you all of that plus debugging. There is a 5th level of output too that gives even further debugging information that the Sundials development team we use internally, but maybe you find it useful. So we set the output location for the levels through environment variables as one way. There's also a Runtime API. And then you can run any example or your Sundials code and see the output. And in this case, this CVODE serial example, I want to see informational output. So we set this sunlogger info file name environment variable to standard out, and then run the code. And we see all of this information is printed out to screen. And in this case, so it's the output is structured so that you have the level of output. So error, warning, info, debug. So that shows up here in the leftmost brackets. Then the MPI rank, in this case, it's just a serial example. So it's saying -1, just saying it's printing on all ranks, the default rank. And then the scope is in the next brackets, and that is typically what package and then the function. So in this case, this is happening in the CV step function internal to CVODE. And then there's a label, and the label is differentiates different sections and functions. And so in this case, it's saying this is the interstep attempt loop. And so at step 0, it gives us step size, the order, and the time that the integrator is at. And you can see then it proceeds. We see output from the nonlinear solver, and then the linear solver, and then error tests for Sundials, for the CVODE integrator, and then so on. And so this information is very useful for debugging performance of the integrators, but also, the other output levels like errors and warnings may be useful for normal use. Right now, like I said, the logger is not enabled by default. You have to have this option set to 1 or higher. But if you do set it to 1 for errors, you'll see output from you control where the error output goes from Sundials using these environment variables. In the future, perhaps the error output may all go through this interface, but right now this is completely optional. So the logger runtime API that you can use instead of the environment variables, demonstrate here in this example code, which is linked down here. And this is a MPI parallel example. So we create the sunlogger object. We give it the MPI communicator, actually a pointer to the MPI communicator. Tell it to output on process 0 only. So once we create that logger, then we can attach it to the sundial simulation context with sun context set logger function. And then we can set the file names for different level output. So we can set the error file name, warning, info, and debug. And you notice here that these are all guarded with these if statements. So if sundial's logging level is at least the error level, then we can create the logger and we can set the error file name. If it's at least the warning level, then you can set the warning file name, etc. If you don't do these if checks, then if you check the return value, for example, for setting the warning file and the logging level is less than warning, then this function is going to return an error code. And so this check of the error code would actually abort the program. And so that's why in this example code, it's using the if statements to make sure that it's only using the functions when appropriate. And then lastly, these print all stats functions that we've added, which are separate from the logger and the profiler. They print integrator and solver statistics. A lot of them are statistics that maybe you're used to seeing when or being able to get from sundials using our various get functions. But this provides a way to print them out in a human readable or machine readable format. In the machine readable format, it's supported to CSV. And then there's also statistics here that maybe you haven't seen before. And so in this example, we're in the link to this full example is down here. It's a example from ARKODE using the MRI and ARC step modules. And so we have an MRI step print all stats function that's printing in the table output format, which is the human readable format. And then the ARC step print all stats, same. And then we do the same thing, but using the CSV format. And so what does that look like? Okay, so we run the example. On the left here, we have the human readable table format, showing things like the current time, the number of steps that the integrator took, stability limited steps, accuracy limited steps, etc. Then optionally, as you saw, we also print out the CSV format in this example. And so this is just a duplication of the data you see in the human readable, but in machine readable CSV format. And so with that, that concludes my part, and I'm going to hand it back over to Dan to talk about the Scalable demonstration code.
Okay, thanks, Cody. So I understand that it's been kind of a fire hose of a bunch of information. So I'll try to finish up in plenty of time to leave room for questions, and we'll all be on so you can ask questions about anything. But I'm going to focus for the remainder of this my part, and then Carol will have some closing remarks on the Scalable demonstration code. And so this is a code. It doesn't use everything we've talked about already, but it does use multi-rate, it does use GPU. It should use the performance profiling stuff, but I haven't added that yet. And so we'll, but it kind of contextualizes some of these things and lets us see a little bit about one of the use cases that we kind of envision. So with that, let me just remind everybody, if you attended our tutorial a couple years ago, you learned about our new many vector, and this demonstration code really leverages that in a variety of ways. And so I'm not going to reteach everything about the many vector, but just to highlight what it is it's a really thin software layer that just provides the concept of a vector for really an array of separate subvectors. And so we have two flavors, a regular many vector and an MPI many vector. At the heart of them, both of them just have an array of pointers to actual n vectors that store data. So neither of these store any data. And the only difference between them is really that the MPI many vector also has a communicator. And so it could be an intercommunicator for really complex, maybe each of these do some MPI on a subset of the machine and this intercommunicator connects them together. Or it could be that these are node local vectors. And the only way that the Sundials integration might know about the parallelism would be through the communicator that glues them together for norms and dot products and things like that. And so the operations that happen in here, like you want to do a dot product, it will ask each of the subvectors to compute its portion of that overall dot product, and then it will do the reduction. It'll add everything together here or add everything together and do a reduction over here. So this is the idea of the many vector, and it's really thin. It doesn't have much weight on its own right, but it really can allow us to do some interesting things. And so, for example, one thing that we're going to use in this demonstration code is it allows us to stage different parts of the solution on different types of hardware. So we can have some things that are staged on CPU and maybe other things that are staged on the GPU. And so that's one of the things we're going to do in the next couple of slides. Okay, so this demonstration code, it does reacting flow. So these are the 3D nonlinear compressible Euler equations. And so that's the transport of stuff. And the stuff itself consists of stiff chemical reactions for a low density primordial gas. And so these are going to be molecular and ionization states of hydrogen and helium with free electrons, internal gas energy, those kinds of things. And so this is a relevant model for maybe things in the early universe. But again, here we're trying to show how Sundials kind of works. And so, I'm not going to focus too heavily on exactly where the this ionization early universe problem comes from. So mathematically, it'll be an advection reaction problem. So we have a time derivative of W. We have divergence of fluxes, and this will be the nonlinear compressible Euler equations, and we'll have some local reactions with no spatial derivatives on them. And so W will be a vector that contains density, momenta, total energy. So 5 fields for the fluid flow, and then 10 more chemical species corresponding to all these hydrogen and helium ionization states. And so F will be these advective fluxes. We think of these as being non-stiff. Everybody in general does advection explicitly, and that's going to be the same here, but also that this happens more at the slow time scale. And so we're going to think about that as being a slower process than these reactions that can occur incredibly rapidly. And so those will all be encoded in this reaction network. These happen on a fast time scale and they're stiff. And so, for example, if you think about flow as a warm region goes through the domain, you might have a cell that was cold, and at which point it had one kind of near equilibrium configuration of hydrogen and helium. But as that warm front moves through, suddenly that previous configuration of hydrogen and helium is completely non-stable, and it has to really rapidly achieve a new kind of near equilibrium. And so these reactions can occur orders of magnitude faster than the advection really occurs. We store all of this as an MPI many vector. And so we stage all of the fluid variables on the CPU. So these are held in main memory. And each of them is actually stored as a serial n vector, which is just kind of stride 1 memory accesses in RAM. But the chemical species we store in the GPU. And so for that, I use an n vector Raja. And so it's kind of a generic interface, with the idea being that we'll be able to run this eventually on using HIP underneath, or CUDA underneath, or one API underneath. All of this will be using CUDA. And the n vector handles the MPI collectives. So things that the integrator needs to do, norms, dot products, those kinds of things. Though obviously this advection of the operator, we need point-to-point communication to figure out neighboring exchanges for computing the fluxes. So this is kind of the basic setup of the problem. Oh, the solver strategy, we use a standard method of lines approach. The spatial domain is a box. The time domain is kind of a normal time interval. We use a regular grid that's nx by ny by nz in space, and it's parallelized using standard 3D MPI domain decomposition. Use a 5th order accurate FD-Wino scheme for flux reconstruction of that operator. And so that's highly nonlinear. It's not at all something we'd want to solve implicitly, because it's really nasty. And so we're going to see explicit treatment of that operator in a moment. After we do spatial discretization, we have an initial value problem system of W dot is equal to F1 plus F2. And so both of these are autonomous. There's no T dependence. And F1 is going to be the advection operator that we evaluate on the CPU, just like we store the data in main memory. Whereas F2 contains this reaction network, and so it's going to be evaluated on the GPU, and all the chemical rate tables, et cetera, are all kind of stored in GPU memory. We're going to think of two forms for time evolution: time adaptive third order out of Runge-Kutta IMEX method from ARKStep. And so that's going to be where both advection and reaction use the same time step size in an IMEX formulation, where the advection is explicit and the reactions are implicit. It'll be third order, and it'll adapt the time step sizes to meet accuracy requirements. We also will think of a third order explicit MRI-GARC method from MRI-step. And so the fast time scale, which will be reactions, will use time additivity, and they'll be solved using a diagonal implicit Runge-Kutta algorithm that's third order. And then at the slow time scale, we use an explicit MRI-GARC method, and we think of that as being explicit. And so we're going to specify the step sizes we'd like to use there. So once we've identified what's implicit, what's explicit, we actually have to solve the implicit problems. And so in the IMEX approach, at each stage within the IMEX method, we need to solve a nonlinear algebraic implicit system. And so the implicitness is in blue, the explicit stuff is in red. And by explicit, we have old time step value, but we also have right-hand side values of advection and diffusion at previous stages. And so all of this is kind of data, doesn't affect the nonlinear solve itself. But here's where the nonlinear solve really occurs. And so we see that the stage we're looking for is the I both here and as an argument to the reaction term. So this is an implicit problem that has to be satisfied. Now, the nice thing about this is spatially local. The reactions occur only on a per cell basis. And so if you think about the nonlinear system that arises from this blue stuff, then when you discretize, when you use Newton's method applied to that, the Jacobian you get will be block diagonal. And so on a processor by processor basis, the overall Jacobian for this thing is going to be separate on each processor. But more than that, even within a processor, it's cell by cell block diagonal as well. So each of these little blocks is 10 by 10, corresponding to the reaction network that really occurs inside this operator. So to solve these linear systems, we use a custom Sunlinear solver that solves each one of these rank local operators. So one of these J's, using Sundials' new GPU-enabled SunLinSol Magma Dense interface that David talked about earlier. And what's relevant here is that when we call that on each MPI rank, there's no communication to solve one of these guys. But because this is a custom linear solver that happens for the global nonlinear problem, we do need one MPI all reduced to gauge whether we succeeded or failed at that implicit solve. And so all of our solvers have to say whether we succeeded or failed. And so this one flag has to come back, and that's going to be an all reduced call. Okay. So in the multi-rate approach, at the fast time scale, when we do substepping, we solve these fast initial value problems like we saw maybe an hour ago now. And so each of these fast problems will have the reaction network here and a forcing term. Now this forcing term used the advection operator, but it doesn't need to evaluate the advection operator again. And so there's no dependence on V. And as a result, there's no spatial coupling between each of these ODEs. And so we actually have NX by NY by NZ decoupled 15 variable IVPs. And so at every spatial cell, there's a completely decoupled initial value problem. So to solve that, again, this happens in this MRI context. So we solve these fast ODEs, and all we have to do is solve it and come back to the MRI method. And so for these fast inner solves, we make a custom MRI step interstepper, and it's going to solve all of these almost completely independently. It's actually going to solve all of them on one node in one MPI rank together in lockstep, but then a separate MPI rank will do its own batch of them. And so they could be doing separate substepping in each rank. Now, the challenge here is that when MRI step passes the forcing terms or even the initial condition to the ARKStep integrator that happens at the fast time scale, they're passed in as MPI many vectors. And so they know about the parallelism across the machine. But we want to do these separately on each rank so that they don't know about each other. And it's really easy to do that because it's an MPI many vector. We just access each of the subvectors. So this is just an array of pointers to n vectors that we pull out of the initial condition, for example. And then we repackage them as a many vector. So we pull them out of the MPI many vector and package them as a many vector. Again, we're not copying any data. We're just taking the pointers to each subvector and thinking about it differently. And this Y-loc vector is what we evaluate separately on each rank. And so on each rank, we have a completely decoupled nonlinear system. So those use Newton's method. And then the linear solves they need to do are exactly the same block diagonal thing we saw in the previous slide. So those again use that magma dense batch solver interface. And the only synchronization we need across the machine is an all reduce that occurs now at the slow time scale, not at the internal linear solver level, but at the end of trying to solve each of these fast initial value problems. Did we succeed at solving this problem on each rank or not? And so there's an all reduce kind of at the slower time scale. So just to see some results, these are from Summit. These use 1 MPI rank per GPU. And since on Summit there's 6 GPUs per node, I use 6 MPI ranks per node. For the multi-rate solver, I specify the slow step size to be proportional to the CFL condition for the advection operator. Both approaches use that time additivity at the fast time scale for the multi-rate or just in general for the IMEX. And what we can see on the bottom, these are the algorithmic scalability. So number of times we've called, number of time steps we took, number of times we called the advection or chemistry operators, setups, et cetera. And the relevant thing here is all these lines are flat. And so what that really tells us is that we get good algorithmic scalability, that the algorithms we chose map well to the problem we want to solve. We're not increasing in iteration counts as we grow in size. So that's kind of a good prerequisite for overall scalability. And up on top, we have runtime. And so what we can see a few things. IMEX is on the left, multi-rate is on the right. The scales are quite different. So the 24 rank problem in IMEX takes 2,000 seconds of wall clock time to solve, whereas the 24 rank multi-rate one takes 32 seconds to solve. So it's already a speed up of about 70 just from moving IMEX to multi-rate. And it's obvious what the difference is here. Almost all the time in the IMEX is evaluating that advection operator. So that happens at the slow time scale in the multi-rate, but it has to happen every time step for the IMEX. And it's costly. It has this fifth order we know operator. It needs point-to-point communication, lots of stuff. And so it's just called a lot more frequently in IMEX than it is for multi-rate. And as a result, by pushing the evaluations of the advection operator to the slow time scale that happens so much less frequently, we save a lot of cost. And so the blue is much smaller here. Starts about 7, I guess, as opposed to about 2,000 there. We also notice a couple things about scalability. So the IMEX method scales pretty well until we get up to about a little over 1,500 MPI ranks, up to 5,000 MPI ranks. And the slowdown really comes due to this MPI block. And that MPI block is that synchronization. It's only timing that all reduced to say whether we succeeded or failed. And that shouldn't necessarily be a big slowdown, but what it really is measuring is that the GPUs that we're all doing their local solves have to finally agree that they're all done. And this is where we feel that synchronization cost of the GPUs coming back and kind of synchronizing at the overall problem level. And so this is pretty much just pure GPU synchronization cost. In the multi-rate one, we still have a slowdown due to that. It's this green one, but this is at 24,000, so much larger scale, and it still doesn't overall slow the code down by that much. So we go from 32 seconds to about 43 seconds. So it's certainly not very bad at all. And the reason why this slowdown that we see here, this overall height of the green is much smaller than the height of this green, is because we're doing these synchronizations at the end of each at the slow time scale. For each slow stage, we decide whether we succeeded or failed, as opposed to doing them at every linear solve inside of every time step that we need to do over here. So there's so many fewer synchronizations across the GPUs that the multi-rate really gets to much larger scales. So that's about that for here. And then I'm gonna hand it off to Carol. I'm gonna keep moving my slides, but Carol's gonna talk, but feel free to ask me questions about this or about anybody else's stuff when we get to the end.
Great, thanks everybody. I just want to make a couple of quick comments. Nope, can you? Yeah, thanks. If you can leave that up. If you want to learn more about Sundials, you can visit our website. We have a nice website on the LLNL projects page. You can also visit our GitHub page, where we've got our full repo now, and you can also get this tutorial on our ECP project Confluence tutorials page, and soon we will have the tutorial also up on our publication, the Sundials publication page at the LLNL site. Towards the bottom, we have a list with some presentations, and it has our prior tutorials, which had more of the basics of how to use Sundials. We have a poster on Thursday here at the ECP during the Software Technologies poster session. And then we also have a breakout session Wednesday morning. And for those of you who are on the West Coast, we apologize. This was not our doing for the scheduling, but we are early in the morning on the West Coast. But we do have a breakout session where we're going to have 3 of our users talk a little bit about their experiences with using Sundials and their use cases and such. You can also send any of us an email. We also frequently do WebEx discussions with ECP users to go through interfaces and discuss use cases. If you want to use Sundials, but you're not sure it's a good fit, we're happy to talk with you more about your application. Go through, what your needs are, what you've tried, what hasn't worked, what you think might work, and get a feel for whether or not, and help to get a feel between us as whether or not Sundials might be useful. And if it is, then how you might be able to engage with it, and what the right course of action would be. So we frequently do those sorts of discussions with folks. We're happy to talk with folks about that. Again, Dan characterized this as a bit of a fire hose. We apologize. We wanted to have a place where we got some of these newer capabilities kind of out there a little bit for folks to learn a little bit more about them. We're happy to stay on as long as the ECP folks will let us, answering questions. So I'll turn it over to the audience here. If you guys have any questions, we're happy to answer them. And one more request, if you haven't signed in, to go ahead and sign in. There's a link in the chat. I'll put in one more time. All right, thanks. Are there any questions?
I'll note one more thing while you guys are gestating on questions. Cody had a lot of good links in his, and I forgot to put links at all in mine. So I did put in the chat, I put a link to the GitHub repository for the demonstration code if you want to look at it or play with it at all. And so that's certainly accessible as well. It's like Slaven has a question.
Yes, this is amazing work, and every year when I listen to this tutorial on Sundials, I'm always impressed how much work has been done since the last time. So congratulations, guys. One thing that I would like to ask, all of this great work with multi-rate integrators and partitioned integrators, it is a little bit slow to find its way to some of the DOE's applied programs where operator splitting, aka co-simulations, still rule and dominate. Can you speculate what do we need to do in order to raise awareness of this capability that you have developed, and what would be the proper technical off-ramps to bring that capability to applied programs?
Well, I will answer first. Maybe Carol will have some things added. But I mean, I think one of the first things is just making the utility available. So far, before we released MRI Step, there weren't, as far as I could tell, almost any codes that you could download and start running your stuff on. And so it seemed like a really great place to put it inside of Sundials, where people have interfaces to other things. We try to make it easy to hook Sundials into existing codes. So, step 1, get the software out there and hammer on it some. And then step 2, give talks like this, where potential users might be interested to learn about them, work with folks to get it into their codes. But yeah, right now we're on that, the hard part really of talking with people and getting things into projects and that sort of thing.
And I think as we have successes and failures, to get out and talk a little bit more about them, right? So we are, the Sundials team is actively engaging with a few different applications right now in getting, trying out the multi-rate within their applications. And as we get more results from those, we'll be able to bring those into discussions like this and the breakout that we have on Wednesday. Although I don't know that we have anybody talking about multi-rate in the breakout this week. Certainly we have a few applications that we'll be ready to talk about some results very soon, both in fusion and in quantum dynamics.
Yeah, we are trying pretty hard with these SIDAC calls that are coming out to meet with people and get into their stuff too. So
cool, thank you.
Any other questions? If there are no questions, that's fine. We can stay on here and have some informal discussion if anybody's interested. Thank you to those who've signed on to the interest or the sign up sheet. Got that. If you have any questions next week, next month, later today, feel free to get in touch with any of us. We're happy to talk with you and interact more on your application or whatnot. So thank you all for coming.